What's up, scholars? Today we're going to jump into Unit 7, Circular Motion and Gravitation. This set of notes is going to focus specifically on circular motion and centripetal force. So we'll jump right in. So circular motion and centripetal force are really one of my favorite topics. It's one of the most useful topics outside of just your basic forces and energy, which is why we're covering it right out of forces, energy, and collisions. So it just covers all kinds of things. Here you can see a fair ride, the Ring of Fire, one of my personal favorites, and then all these other things. In your car, the speedometer, the odometer, record player, which are for some reason coming back into fashion, washing machines, satellites in orbit, roads, bridges, roller coasters, fun at the state fair, all kinds of applications. And once you start to notice how much circular motion is around you, you're going to see it absolutely everywhere. So one application that I ran into this summer, I was riding my bike around a rural part of Wisconsin called Door County, and there's all kinds of curved roads there. What was kind of interesting is that this county road here, County Road ZZ, didn't actually have a speed limit sign associated with it. This is a pretty steep, sharp curve, and as you might know, it snows a lot in Wisconsin. So what should the speed limit be? You can actually figure that out by taking a couple basic measurements. And what minimum speed limit should we make it in case it's icy? Here's another kind of interesting question we'll see here. Got a record player here, two little astronauts. So first, how do we know how many revolutions per minute to make the record go at? There's the outer astronaut having a lot more fun than the inner astronaut. If you've ever been on a merry-go-round, you know the action happens. I'll pause there. In that the action happens the farther you get away from the center of the merry-go-round. Who's going faster? Maybe you can tell from the video. Who's going faster, the outer astronaut, the inner astronaut? And then, importantly, how can I turn that into artificial gravity? So this is possible. If you've ever seen the movie Interstellar, there's actually lots of space films where this idea is featured. We can actually turn this into artificial gravity. You can feel the effects of gravity out in the vacuum of space where there's no massive bodies around. Kind of wild. And then, before we jump into notes, the last thing I need you to do is to grab something circular. We're going to be drawing lots of circles. Friends don't let friends draw sloppy circles, folks. So I'm going to be using the top of this wasabi peas can because I was just snacking on them before we started notes here. So grab something circular. We'll get started. So if you haven't yet, go ahead and get out paper and pencil. We're going to be taking some notes. You can see I've got the top of my can of peas, which is going to act as my circle. We're going to start by drawing a nice even circle. So once we've got our circle drawn, we're going to try our very best to locate the center. Now on my little pea lid, there is a center there. So I'm going to use that to try to help me find where that might be. It's somewhere in this kind of area. Not too bad. And then what we're going to do is we're going to draw our first part of the circle. You know the radius. And to help me draw a nice radius, I've got my school ID. So we'll draw a radius. The radius goes straight from the center out to the edge. We'll label that with a little lowercase r. And what we're going to do is we're going to imagine that we have an object moving around the circle with some uniform or constant speed. So we'll say that it starts at this location with a speed v1. Now, we're going to actually say that that's a velocity. And we'll give it a vector hat and some length there. And then what we're going to do is we're going to let some time elapse. And our object will move its way around the circle just like we saw our little astronauts doing that. So I'll draw another radius somewhere kind of arbitrary over here. Oops, I didn't want that to be red. We'll make that black. And so we've gone some amount of angle. We'll label that here. We've gone some angle around the circle. And we're at some new location. What's interesting here is that the velocity is actually going to be perpendicular to the circle, and it's going to be perpendicular to the circle over here as well. We'll label this V, oops, I want that in red, V2. I want that to be the same length, but notice that it's pointing in a different direction. So we'll label this V2. after we've gone through some angle. Now, I'm going to introduce a couple of variables here. You already saw we introduced the radius, some velocities, and an angle measure that we've traveled through. The next one I'll introduce is actually a new Greek letter that we've not used so far called omega. So omega is the angular velocity. This is how we draw that. It kind of looks like a swoopy version of the W. So this is the Greek letter lowercase omega, and it's going to represent our angular speed. Okay, and now what I'm going to do, you saw me write this over here a moment ago, we're going to make some assumptions when we do uniform circular motion. So you can see I just added the omega there. That's the Greek letter. The first assumption is that the radius of the circle is a constant. Things get very complicated when you change the radius, so we're going to leave that constant. The next thing that we're going to assume for right now is that the angular speed, omega, is constant. And then we're also going to assume, for sake of making life easier, that the speed is constant. So v here is going to be called the linear speed. V is constant. Now I'm being very precise here in saying speed, not velocity. Very important, we have changed directions from here to here. So though the speed is staying the same, the velocity is constantly changing. So, important note, make sure you pause and get this down. Though the linear speed v is constant, the velocity is not. The direction is constantly changing. So that's going to lead to us having acceleration, which we'll get to shortly. To go back to our example here, let's check our assumptions and see if they're correct for our astronauts and all parts of the record. Let's check that out. So the radius, the distance that they are, mute that, away from the center of the record, the distance r is staying constant. We'll pause it for a sec, you can see that. So the distance that they are away from the center never changes. The radius is constant. Next, the angular speed. How fast are they moving around in a circle? Or in other words, how much angle are they going through each second? That's the omega, that funny new symbol. We'll define units and stuff in a moment, but it's constant here. In fact, if it wasn't constant, what you'd hear is the record would be going up and down in pitch. And then finally, we don't have a good way of measuring it here, but is the linear speed v constant? Well, it turns out that that's tied very much to the angular speed. And so if the record sounds normal, that actually tells us that the linear speed is normal. Let's check it on the record. Yeah, that's how the zombies are supposed to sound. So let's get some definitions before we wrap up this first brief set of notes. The first one is the Greek letter theta. And we're going to define that a little bit differently than we've talked about so far, or that you've learned about in your math classes. We're going to think of it as an angular distance. So instead of going in a straight line 1 meter, now we can go around a circle some angular distance. Often I'll slip and call it angle, but we really want to think of this as a unit of distance, just going around a circle. So we'll write that definition down. So how far you've gone around a circle, that is your angular distance. One entire rotation or revolution, right now we can use those words interchangeably. One revolution is equal to, you guys know this, it's equal to 2 pi. One time all the way around a circle is 2 pi radians, or just 2 pi for right now. Now, if you're not familiar with the concept of radians, it's really simple, probably simpler than you think. It's the same as saying 360 degrees. So if we went halfway around a circle, you know that's 180 degrees. If we went a quarter of a way, you know that's 90. For various reasons, it's helpful to split how far in angle you've gone around the circle into 2 pi. Radians is the unit that we use. So for example, if we went halfway around, well, that's half of the whole, so it's pi radians. You can split that into quarters, eighths, whatever you like. So next you've got our friend omega. Remember that was angular speed. Just like linear velocity, regular old velocity, is distance over time. Angular speed is just angular distance over time. Now, we like to write that in a sort of special way. So first we can say in general, this is in general, omega is theta, that's the angular distance, over little t for however much time you want. So for example, I'll just make this up. Let's say we went 120 degrees in 5 seconds. You can do the math and work out how many degrees per second you went through. But what we normally like to do is say, okay, what if we do just 1 revolution? When we do that, well, we can define omega just like this. 1 revolution, we said, was 2 pi radians. So omega is 2 pi. And then normally when we talk about something completing a cycle, we use capital T for period. So this is actually how we're going to define, for our purposes, omega, or the angular speed. Very quickly, let's get the units. So we said that 2 pi is a measure of radians. We'll often abbreviate that to rads per second. So radians per second is how we measure the angular speed of something. We'll do some practice with that. Just for context, radian is actually unitless. So this is really nothing units over seconds. We'll get into that a little bit later. All you need to know is that for right now, anytime you're doing a calculation with this equation, it should be in radians per second. Now we've got 2 more quick ones. Linear speed. Now, I'm going to be mixing up speed and velocity as we go. For right now, I really do just mean linear speed. Up here we were talking about velocity because we care that the direction changes. But for our purposes, I want to really relate angular speed and linear speed. We'll get to the velocity just a little bit later on. So anyway, linear speed, let's compare it to angular speed. So we had angular distance over time. Well, not surprisingly, this is just going to be the linear distance over time. Now, you might be thinking, okay, well, what's the linear distance around a circle? That's just, what is it? The circumference? Yeah, I taught geometry over the summer. The circumference is all the way around the circle. So whatever object you picked to draw your circle with, imagine putting a tape measure all the way around the outside, stretching it out. That would be the linear distance to go all the way around. So our V would be just the circumference. Let's see if I can spell that correctly. I think that's right. Over the total time for 1 period. So that ends up being 2 pi r. You might remember that that is the, 2 pi r over capital T. So that is equal to, we'll squeeze that in here, that is equal to V. The linear speed is 2 pi over r. Now again, here's where the units come into play. I kind of mentioned we can ignore radians as a unit, so on top we just have meters, r for radius, over t, the period seconds. So this just ends up being meters per second, which is what we'd expect from any kind of linear speed. Alright folks, the last thing we want to do is we want to relate omega, our angular speed. Well, let's put, let's underline those. These are important. Angular speed, omega, and linear speed, v. So I've written their definitions here, and I'm hoping that you can see that omega is actually hiding in v. Can you see it? If you can't, it's actually hiding right here. So what we can do is just simply replace 2 pi over t with omega. So what that means is that v is omega r. Or we can solve for omega as well. So just divide both sides by r, and we get that omega is v over r. Check my work there in the algebra. That is how we can relate the two of them together. Let's do a quick concept check to see. This says that if everybody has the same omega, the same rate that you go around the circle, your speed should increase with r. Let's check that by heading back over to the record player. So both of them are moving at, I'll just spoil it, 33 RPMs, or 33 revolutions per minute. 33 1/3 if you're a record snob. Now, that means that they have a constant the same omega. So ask yourself, take a look at the video, I'll even let the music play, which one's going faster? Well, if you look carefully, you can see that this one has a little bit more motion blur than this one, and that actually means that they're going faster. Another way to think about it is that this one has to go all the way around this big circle in the same amount of time that this one has to go around the little circle. So in fact, the reason it's more fun to be on the outside is because you're going faster, and as we'll see, that means that your acceleration and the forces on you is much larger. So there it is, folks. That is your quick introduction to uniform circular motion. Thanks so much.